calling this the HPC X Games or Extreme Scale. But the topic is issues and experiences in getting to extreme scale. You've heard several speakers here talk in terms of hundreds of thousands or even millions of processors, millions of MPI ranks that they have run codes with. And so I just wanted to sort of bring that back, as speakers have already talked about real problems they're solving today. But one problem, a real scientific problem that's of particular interest to me, and I wanted to mention it because it's very recent results, some calculations from LIGO. So real quickly, who knows what LIGO is? A lot of people, about half. Well, that's great. I only learned about it recently. When I heard about it, I was just so fascinated with what it is. It's basically an instrument that has detected gravitational waves, something that Einstein predicted over 100 years ago. An aspect to this process was a lot of computing, because there's this large interferometer that's sitting there waiting to be disturbed as gravitational waves pass through it. And the question is, it's such a small signal, they have to do a lot of pawing through volumes of data to actually figure out if something really happened. So they maintain anywhere from 5, I couldn't really get a good estimate, in spite of looking everywhere, of how many teraflops they actually need to do this. But it's sustained roughly 24/7 a week of 5 to 35 teraflops to actually compute the detections that LIGO predicts or detects. It's an embarrassingly parallel problem. Bottom line, it's basically searching for a matched filter. So you can imagine somewhere embedded in these signals is a real signal of a gravitational wave, and the way they're detecting that is sliding a filter over it. A lot of different filters, though. It turns out that they had 2 detections, one back in September of 15 and one in December. And I've heard recently that they think they even had a third in February that they haven't reported yet. And this is just some of the data from the 2 detections. A very fascinating result. But here are the kinds of questions that I think we'll cover during the panel. The first question is LIGO really high performance computing, or is it cloud computing? And what's the difference between those? So our panelists, I've already sent them these questions earlier for them to think about. These are the questions I've thought about asking. But again, during the dinner, I would like all of you students to feel free to ask questions on the topic of what it takes to get something really working at extreme scale. And again, the topic is on sort of issues and horror stories and interesting processes in getting to exascale, extreme scale computing. So with that, I'll open it up for questions for our panelists. Don't be bashful.
Surely somebody wants to hear a war story. You can just ask, what's the worst experience you ever had? What's the worst experience you ever had?
As probably many of you have encountered, programs often have bugs in them, and it's sometimes the case that bugs don't manifest themselves on small number of processes, but rather large numbers of processes. So there have been a number of cases where users of the PETSI software have encountered problems that haven't shown up until many thousands of cores, and so. We've learned a lot about strategies for coping with those and debugging. I would say, one thing that has changed over the years is more people are consistently using tools to help them with checking that they're using memory appropriately, tools such as Valgrind. So we had much fewer incidences of seg faults and weird things happening on huge numbers of cores when people are doing a really good job as they're going along on small numbers of cores with debugging. So that's just one thing to keep in mind.
So I'll ask each of the panelists, and on that topic, how many of you encountered situations where your code is breaking, but only breaking at that significantly large enough scale that it's a real pain to try to debug it? Okay, so everybody's
how many in the audience have encountered that?
It's pretty rare, but yeah.
Mark says he finds bug on one processor to be a pain.
I would echo what Lois said, though. If you use good tools and development practices ahead of time, you can do most of that on very small numbers of cores. And the large-scale issues like that really don't happen that often if you do things right to begin with. But we've all had to deal with them once or twice or 3 to 4 times. And it's hard when that happens. But.
Matter of fact, to amplify that, and I don't know if the experience is consistent with all of you as well, but I work on a visualization tool called Visit, and I would say 98% of all Visit development occurs on a laptop, but it scales to very, very large scale. So it's I think that's true of PETSI, it's true of all the codes here. all the development's typically done in a pretty small machine. So.
I would say that, is this something running? All right. I would say that it is much more common there's correctness debugging, and that almost happens, most logic bugs are, run it on 2 ranks or 4 ranks. You'll discover it. Correctness debugging happens less at the large scale, but performance debugging grows and grows. So even when your code runs awesome at 1,000 cores, and then goes into the crapper at 10,000. At 10,000, you get it all working out, and at 100,000, it only runs maybe 3 times faster than your 10,000 job, right? So at each epoch of your scaling jobs up, you tend to have to find all new scaling problems and all new performance bottlenecks. And I find that more often than not, a lot of your kind of profiling tools to tell you that this is happening lie to you. So it's usually good to have more than one way of profiling your code. So put in your own time function occasionally just to give you a sanity check. So when when CRAPAT tells you one thing and HPC Toolkit tells you something else, it's like, okay, I don't quite know what's wrong yet, but I know that overall my code didn't go any faster. That's bad. So that's my bigger horror story. That's my ongoing, recurring, and it's going to happen again with my next level of scaling up. So that's where you spend most of your time.
Right. Echoing some of those comments, we work on unstructured meshes, and when you get out to really large scale, you get new or different topological structures that don't occur at small scales when you have sort of saturated connectiveness between different parts in the mesh. And debugging those can be quite difficult, and having tools to extract out those neighborhoods or those individual parts which are causing problems are pretty critical. But as these folks have said, debugging and doing correctness checking as you go up the scale is critical, so you have as few of those problems as possible.
I think it's also really important to keep open your flexibility in changing algorithms as you increase in size, because oftentimes you'll find that what you're modeling changes as you change fidelity, the physics changes, and the needs that you have in algorithms may change as well. So you want to not lock yourself in to only one solution.
Okay, any follow-ups? Go ahead. Sure.
So I'm curious what you guys think about how you would recommend. Where I come from, we don't have we're not part of a big project like PETC or something like this where you can start kind of working with already developed, code sets. And so a lot of our research is kind of homespun, right? And you have this idea and you code it in serial. Maybe if you're ambitious, you develop a parallel program, but you're not going to be able to scale with that very well because there's years and years and years and years of development that needs to go into that to do that well. So I'm curious, what's your recommendation for folks like if it's learning PETC? I think it's getting better, but there's a steep learning curve, I think, right? So to get in to just toy around with an idea is, at least in my experience, would be hard. So I think there's a place for playing around with ideas and algorithms, and then at some point, when do you start implementing or trying to implement those in something like PETC or a much larger, well-tested framework?
Well, that's a great question, and it's a situation that many people encounter. So I certainly understand the learning curve issue that you mentioned. In my personal experience, I would advocate investing in trying out some examples in software infrastructure and playing around, getting familiar. Actually, it doesn't necessarily take as long as you might think, and then build on top of well-tested and robust infrastructure that can handle some of the details that really you don't want to spend your time tackling, like direct message passing code. That doesn't directly answer your question, but I think the investment in something is worth your time generally.
I'm sorry. Did another panelist want to go? Okay. Go ahead, Rob.
At the end of your question, I thought I heard you ask how often do we play around with ideas before we actually implement them in our software frameworks? Okay. So there, I would say at least speaking for us on the Hyper team, we do a lot of experimentation using, we do a lot of things with paper and pencil, sort of designing algorithms, writing it in MATLAB, Python, just, doing a lot of studies that don't involve parallel computing. We're always thinking ahead to the fact that we want something that's going to run at really large scales and parallelize and all these things. But it's not until we do a lot of, sort of work on the algorithm before it ends up in Hyper as something that we give to you guys to try to use. So I can answer that question anyway, that part of the question.
So a question I heard over lunch from one of the attendees was similar, and I'll paraphrase it. Yeah. The question was, he had basically asked is, he's already developed an algorithm to go to large scale, so billions of unknowns, and in a fairly specific optimized case. I guess it was a 3 volume, but ultimately is separable into 1D pieces. So n cubed versus n types of calculation. So it developed infrastructure and now algorithm to support that capability. Now, you could do that with PETC, for example, if we wanted to. But you have to remember that things like PETC or SuperLU or whatever, or Hyper, they're designed for more general cases. And so it wouldn't necessarily be able to take advantage of the optimizations that were already known. And in addition to that, would not necessarily be tuned to the data structures that you're already using. And those are reasons why continuing the homegrown effort may be useful for a while. But as Lois mentioned, there's a huge investment in these codes for dealing with a lot of capability that in theory you won't have to use if you were able to just sort of download them and start playing with them. So getting experience with them is real important.
I'd also say that your generation, or the one that's coming up, you pretty much don't have a serial processor anymore, right? I mean, this is already 8. You're going to be having probably 24 to 64 cores on, I'd say in about 10 years, that'll be the standard workstation is about 32 cores, 64 cores. So you're leaving a lot on the table just writing any code, just pure serial. And the barrier here is usually, it's not hard to get that code to run using much more of the cores, because the hardware and the operating system are going to manage coherence for you. You don't actually have to think that hard about the consistency model, like race conditions. You got a little stuff in each of your programming models, like your C language or your C++. You have pragmas. You got a little bit you add onto your code. Now you're running your loops parallel, or now you're running your kind of graph walker parallel, and you have to kind of be careful here and there to do the things right. But you're already up on the parallel curve, right? You're already thinking in parallel that, how do things break apart? And then if you really need bigger, well, you'll get a pretty big computer already with one socket and the memory on it. Like that's already a pretty big calculation if you can use it all. The next stage is, going to something distributed, and maybe we'll have better tools for you by then. But I would say it's already time to think about it even for sitting at the keyboard writing. Like your next versions of MATLAB and stuff are going to be using all the cores, right? So you're already getting parallel computing, and if you're writing your own C or Fortran, you probably want to be sticking in maybe OpenACC, maybe OpenMP, start putting the pragmas in, get some familiarity, start thinking in parallel. The bigger leaps to message passing. Well, now I need distributed memory, right? Message passing is for when I don't have the same address space.
Sorry.
I'll take it. Time's up.
Okay, there's another hand up here.
So related to your point, we should start thinking in parallel, like trying out all these tools that are available on top of standard programming languages like C and Fortran. One of the issues with that is that compiler support for these tools has lagged far behind. So especially, say if you take OpenMP 4, the specification is out, but then compiler support for that hardly ever works out, and even then it's not a guarantee that the compiler implementation would stay true to the specification. How do you guys handle these sort of issues?
So mostly I avoid 4 for now. So I work with OpenMP 3 or 2 point something. GNU, GOMP typically does 2.5 to 3 quite well. GOMP doesn't really, the GNU OpenMP doesn't really do 4 properly. Clang doesn't really have an OpenMP yet, but it's going to have one soon. You're probably only maybe a year and 2 years ago I would have said C++11, forget it, stay away from it. No one's ready yet. And now everyone's there, right? C++11 now can do all the things that standard says, and it works pretty good. So you're only maybe a year, the Intel compiler does OpenMP great, the Portland groups, most of them, I don't have any experience with any of them not doing up to 3 properly, but OpenACC, yeah, it's not there yet. But other pragmas, don't get too fancy with it, right? Don't really ask for all the fanciest bells and whistles like remote fetch add or, this task depends on the nested OpenMP tasking of blah blah blah. It's like you're running way past the kind of current technology. OpenMP parallel 4. That friggin' works for everybody, right? That's a good starting place.
Well, even GPU support is quite shaky.
GPU is a whole other game, right? Right now, I write CUDA, and I will sometime during my career I'll have one programming system for that.
And we are going to be dealing with performance portability tomorrow, during tomorrow's panel.
I can add to that for the MPI perspective. There's a lot of neat and fancy features in the latest specs of MPI, but use them at your own risk because not all machines, especially the very large installations, will have a vendor implementation that supports them well. It may work. You don't know how well it may work. So you may want to have in your code a mechanism to switch out your own implementation of something like an iBarrier or with the vendor's implementation or something, just so you have that flexibility if it is available to use it.
So I'll follow up with that, Cameron. The basic problem is you're talking about a new technology here or a new standard OpenMP4. Walk back 15 years. MPI, is it 15? Maybe it's 20 now. MPI was just coming online as a standard. There weren't a lot of full implementations of MPI. And some people took the risk and jumped to it, and other people were still stayed on the fence until later. I think you always have to kind of weigh those as being on the bleeding edge against what it's going to cost you when the bleeding edge fails you. So, question back there.
Yeah. So as we have heard multiple times this week, the going to exascale will require a special consideration to monitor the energy consumption of our algorithm. So I wonder if you have considered, like we have seen tons of presentations today, and we're going to be seeing more. Mostly we're talking about like reducing communication and getting speed up, which has some effects on energy consumption. But have you done experiments that actually measure the amount of energy consumed by a certain algorithm, and have you actually planned to implement or design an algorithm that's energy aware?
Certainly there are people in the community who are working on that. I'd say that many of us think about data movement, which is directly related to the energy consumption and the overall cost. And so a lot of us think in our algorithms in terms of trying to reduce data motion. Also, I think at extreme scales, it's really important to be open to thinking of new paradigms, particularly thinking more asynchronously so that we don't need to be in lockstep. You guys may have other things to add.
Well, so Jim Dimble gave a talk earlier. I agree about the data movement comment, where he was looking at lower bounds, right? So if you have to solve a problem, what's the minimum, time you have to move the data, right? So, and if you do that, then presumably you've gone a long way to minimizing energy. And similarly for multi-grid methods, I would say that's true as well. Since they're O of n, they move the data O of n times, which is the right order, the right minimal order. We're not doing anything. I haven't done any measurements myself or tried to develop algorithms that keep that monitor power and things like that, and try to scale back or any of these kinds of things. But algorithmically, we're certainly thinking along those lines, so that we develop the right algorithms themselves to at least give it take a big step towards minimizing power and things like that, power use.
I would say that most algorithms currently are energy optimal when they're time optimal. So almost all your algorithms that you're using today on existing hardware platforms, the energy optimal solution is also the time optimal solution. So we tell people, make your code finish as fast as possible and then get out of the queue. Now you've minimized how much energy you used. You might start seeing platforms in about a 5-year time frame where your energy optimal and your time optimal aren't the same. It's hard to say exactly. Like the new Chinese machine that's come online has that kind of property that if you use the local scratch pad well, your energy budget is very low, but it might not be the fastest code. But the people are looking at that. Currently, what you have in the world is that your latency curve and your energy curve tend to track each other, and latency tends to be what's limiting your time in terms of data movement. So to go from your die on your chip down to the board takes a certain amount of time, and it costs so many joules. Go from the board across the NIC to the other machine is a very high latency, but it's also the highest energy. So while those two curves are not on top of each other, one's a scaling of the other. So race to finish and lowest energy currently look the same.
So on the flip side of that, I just want to add, I know I'm not on the panel, but there's some research at Livermore that looks at what happens when you constrain energy use on a large set of processors. How does that impact how well the processors are running and the speed at which they run? And it turns out that it can significantly impact how fast those processors run, and they don't all run at the same speed at that same energy bound. So now you're adding in some additional complications with respect to load balancing, for example. And so there's a flip side to that as well in terms of we have to think about our algorithms with respect to power, but power can also impact how we think about our algorithms, right? From what we need to do to handle the complexity of that.
So when I try to implement my algorithms the first times in MATLAB or in Mathematica, I usually screw up. So how do you make sure that the stuff that you implemented is actually correct on the large scale?
So when you transcribe from your script world into your kind of your big iron code version of it, sometimes they're getting different answers. Yeah, that's tough. I'll let someone else answer. I just want to clarify the question. That's all.
Well, I would say that many code developers use techniques to try to verify that what they're doing is first of all solving the problem they want to solve, and then solving it correctly. Once you have come up with an implementation that you trust, then you can compare against that. That's what many people do. It's also important to think about using tools to help make sure that you understand what you should expect in terms of performance. So we talked a bit today about performance modeling. That's not testing the implementation, whether your finite element code is correct, but by doing performance modeling, you can begin to understand what sort of performance you should expect to achieve for your code, and then you can compare what you're achieving with that in terms of your actual runtime with what you're seeing. So I think that's an important aspect of looking at correctness as you're going to full scale.
Something I've been curious about, Lois, are there cases where you might have analytic solutions to real simple PDE that then you know what the answer is, and then you can also have PETSI run it? And are those helpful at all, or are they kind of useless?
Oh, sure. That's a great approach. I'm sure many of us use that with our test cases, where you can start with something where it's simple and that you understand, that's correct, and then make changes to gradually move away from something that works to something that's more complicated in increasing steps.
Is there another question back here?
I'll throw a comment on there. As you're developing the code in the target language, certainly write tests and keep those running as you incrementally make changes, because those tests will prove a huge time savers when somebody else contributes something to the code and you're not sure if it's correct or not. And
So
as
I'm
appropriate.
really glad Cameron mentioned tests because unit testing and then progressively testing more complex scenarios is very, very important so that not only you get correct code at one point, but it remains correct over time. And I just like to mention that we have a project called the Ideas Software Productivity Project that is trying to look at practices in software engineering to help with just the general development concerns such as what you're talking about here. And that group is going to be presenting a tutorial at Supercomputing on testing. So there's some resources on the internet, and that tutorial might be of interest to some of you. Ideasproductivity.org is the website for that project.
Okay, question in the back then?
So at exascale, the mean time between failures is going to be very less compared to be now, right? The most optimistic estimate is at least like half an hour or something like that. So do you think that even in our existing algorithms, like best algorithms like multigrid, do we need to think about the fault tolerancy, or like if I am designing a new algorithm, like do you think that I have to keep that into account, or do you think that it has to be tackled at the hardware level? Like what is your opinion on that?
It may be somewhat naive, but for all of the runs, maybe not all, but the vast majority of the runs we've done on the large Q installations, I don't remember one that was directly applicable failure due to hardware. So I'm not sure fault tolerance should be your primary concern. Certainly there's a lot of important research going into it, but it's not necessarily going to be an issue until we see the actual machine.
I will relate one horror story. So this was the original Titan installation out at Oak Ridge, and I was running a code and I was getting difficulty getting scaling. So I had a performance bug. And I looked at my own timers and looked at the other materials, and it would keep telling me, yes, somewhere in here you have massive imbalance in your code. So I started taking functions out, taking MPI calls out, just commenting them out, until I literally had, MPI start, run one piece of Fortran, which everyone was doing the same Fortran, then exit. Massive load imbalance. They're all doing the exact same calculation. So then you start asking more questions. You can run the batch, you can run the queue system and tell me what node is doing what time, like map it back to my rank. You end up discovering that on that one board, on that one processor, one of the memory chips was failing. And because you had ECC, error correction in the software, in the OS, my code would execute. So the machine hadn't failed, but the hardware had failed. It was manifesting as slower. That one node would run a little slower, and it would consistently do it. Now, there's intermittent failures like that happen in everyone's code, and so you kind of start losing your scaling curve on most codes at kind of 10,000 to 50,000 cores. You're going to start seeing that variability. The vendor is not going to let the chip go down or the memory go down because that costs them money. They fail to meet their contract. But they will, all these mechanisms to keep the thing up happen in the OS, they happen in the interrupt system, happening in the messaging layer. You have a lot of fiber between two nodes. Some of the fiber goes dark, so you're going to start getting a little bit less bandwidth over time. In some systems, they get slowly replaced. So it all looks like performance variability. What do you do about that? You need somewhat dynamic execution models. You probably aren't, I did a lot of research on how do you detect soft faults. I tried to do a floating point operation, it just gives me back the wrong answer, right? The worst kind of bug. There's very little I can really do about that. It's a very hard research question. But the simpler one is just fail. And node failure, I think the vendors are going to provide OS migration. They're just going to move your whole process over. You start up on another node, it'll probably pick it up. It's this kind of, it doesn't run quite as fast as you think. And so maybe you need a little bit of resilience to, try to don't do so many barriers. Don't have the messaging, don't have everyone show up at one point and try to do one big reduce, right? MPI, the next MPI has kind of relaxed reductions, like, non-blocking reduce, non-blocking communication, try to be a little resilient to the fact that not all the nodes are going to run at the same speed. That's my advice.
Okay, was there another question about?
Yeah, hi. So I wonder, is the reproducibility on numerical research down on exact scale computing platform, will that be an issue, or will that be a topic in the future? Because I think if I see some research done on exact scale computing, and I want to reproduce that, but I probably cannot afford that kind of allocation. I don't want to spend those allocation on supercomputing just for try to reproduce their result. So I wonder, will that be an issue?
So reproducibility is indeed of increasing importance to our community overall. We want to have trust in our scientific simulations because we use those to inform decision making and science policy, discover new things. So reproducibility as well as software sustainability is very important in that context. So the project that I mentioned earlier, the Ideas Software Productivity Project, is trying to look at issues and methodologies for software engineering, especially keeping in mind high performance and extreme scale computing, so that they're practices that we can all incorporate into our development of code that helps us have more trust in our code. Things like testing, things like using software repositories and using good practices. On Monday, you'll actually hear presentations from a variety of people talking about those issues, but all of those kinds of software engineering and productivity practices contribute to creating code that you can trust and that can help that be reproducible and sustainable.
So, were you going to comment, Rob? Okay. So I want to paraphrase the question because I think I heard a slightly different question. The question was, if we get results that are done on an exascale resource, for example, numerical results from that, and somewhere else in the community wants to reproduce those, but does really not have access to or the resources for an exascale resource, how are those results reproduced? How are they confirmed? Was that part of your question? Okay. So did any of the panelists want to comment on that basic?
I have no idea.
I think if you need an exascale computer to do the calculation, you're going to need an exascale computer to validate it, to verify it. No, what's the right word?
Well, so let me ask a naive question on that. If you did 10 million compute hours for something, and then on an exascale resource, oops, now it's my time's up. Real quickly, 10 million compute hours for one result, and you only had access to a million CPU system, then in theory you could run it 10 times as long to try to, I mean, at some level. Is that a reasonable answer? I don't know.
I think it depends what you're trying to verify.
Okay.
If it has to do with timings, or if it's related to timings and the way the machine actually, functions, then yeah, that's hard without having a system you can run on. Yeah. But I don't know. I suppose you could emulate, an exascale situation if you wanted to just check to see if it depends what you're verifying, I guess. But no, it sounds like a very difficult situation to be in.
There are two kinds of irreproducibility that I'm aware of. One is summing in the different order. So floating point summed in different orders can give different answers. So maybe you're sensitive to that. So there are ways to, we have BLAs, we have MPI functions where you can say, I literally need the same answer every time. It's a little slower, and get the same answer. So that's important for you and someone else when you're talking to each other, then you can have that done. The other case is you have coded a race condition. The answer changes based on the speed at which things happened. I would say the race condition one is a bug, and people need to go back and fix their bugs. So I don't think your science should result on the order of the race condition. There are people who say, well, I want to, have this kind of asynchronous time-stepping type algorithms, and it runs so fast. And I have problems with that because I have a difficulty reproducing it, right? There are people who do particle methods for astrophysics where they don't do the gravity solve that often. They say, it's not that important. And I said, but I have a hard time reproducing your result now, right? You're starting to affect the scientific method. So I'm okay with order of floating point operation summing because that's a artifact of finite precision. I have a bigger problem with my algorithm actually inherently accepts race conditions. I think that's bad, and we should go argue with people about that and review papers and say no.
So is the race condition the same thing as changes in MPI message ordering?
Yes.
Okay.
I think at a very high level, you can address some of the reproducibility questions just by keeping track of what you've done, the metadata, what version of the code you used, how you generated the inputs, et cetera. This will help you in the long run when you try to go rerun that test to see whether the new code does better, or if somebody asks you, where's your data, how did you get this result? I want to reproduce it, or try to.
Okay, other questions?
So at some point there was this idea of mixed precision mathematics in discussion, or one could read about the idea of having part of the solve being done in single precision, afterwards switching to double precision. Is this one of the things which pops up from time to time and will never make it to large-scale codes, or is this something that the FASTMath team actually tries to incorporate into some of the larger projects?
So if you let me jump in, I have an answer that's tangentially related to that might be interesting, and that's the use of compression. We're looking at the use of compression. A researcher at Livermore Labs by the name of Peter Lindstrom has developed some really cool, lossy compression. And the question is whether or not the loss due to compression affects the numerical results of the simulation. He's done a lot of research to show that it really doesn't within the numerical precision of the machine. And that's a way, if you can kind of think about that, is doing some kind of mixed precision, because he takes double precision numbers and represents them by 2 or 3 bits, for example. A lot of compression, maybe 32 to 1. But that's just tangentially related to your question. Panelists, did you want to comment?
Well, one comment I would make, as we talked about today in algebraic solvers, there's really quite an art to effectively preconditioning your system if you're doing an implicit problem. And so there are a lot of ways that you can use lower precision or other kinds of approximations in representing that preconditioner. And that's certainly an active area of research for many, many people. And there are other aspects of simulations also where you can get away with saving memory and such.
Is anybody using quad precision? Anybody know?
I'm not using it actively. I mean, we provide support for that, but I can't comment beyond that.
Okay. I've got a user who just asked about that a week ago. So we might actually provide that capability in Hyper. It doesn't seem like it would be too difficult to provide it, but they have, this is, what's the name of the code? Enzo. Have you guys heard of that code? Where it simulates basically the entire...
It's cosmology code.
Yeah, it's cosmology code, but they have like 25, 26 levels of refinement, things like this, so they have to have super high precision just to make sense of the results. And they were asking about precision and whether or not the problems they were seeing at 26 levels of refinement using Hyper when things were dying was due to precision. And so that did come up recently, and so it's a possibility.
A comment about extra precision. So we have a number of libraries, double precision, which pairs 2 double numbers to give you 106 bits precision. And it's entirely portable because it's just using IEEE double precision standard. So it's not quite the quad. The IEEE quad is 112 bits. And another is quad double, which is 256, four double numbers put together, and then the arbitrary precision library. So you can download all these from our website. And then in terms of support, so I think if you want to use quad higher precision, double is a very good option. So in terms of speed, do a double plus another double, it requires about 20 standard floating point operations. So you would think it's a slowdown of 20-fold. But it's actually not that bad because all these operations are happening. You fetch the data much less, and they are happening at the register level, so you get a very high arithmetic intensity. So we benchmark the sparse matrix vector multiplication of 1,000 by 1,000 matrix size. The slowdown is just like 2, 3 times, 4 times. So it's quite at a pretty good speed. If your code selectively some region, you need to use double-double, for example. And then a related effort is the extra precision, extended precision BLAS. Has anyone heard about that? So everyone knows BLAS, right? So now we have a standard which allows you internally to have inner product accumulation in extra precision. And when you exit the dot product, for example, then we truncate it back to double precision. So that will help a lot of the linear algebra library. And right now we are revising the standard so that we allow the output of the BLAS operation to be also double-double. So it's more flexible, also increase the number of applications that can use these libraries. So that's the about work.
Thanks, Sherry. Okay, we're coming up on about 10 minutes left, maybe give or take. Does any other questions? There's a hand here, Lori.
So you were talking about performance variability both across nodes, and it seems like in future architectures that's going to be a problem even more so across cores, identical cores on a node. And so I think one of the interesting solutions to that are these dynamic runtime system approaches. But I'm curious, are there algorithmic solutions to these kinds of problems, like things you can do at the algorithmic level to overcome this, or basically things other than these dynamic runtime systems, I suppose?
Well, I think overall, as we scale up, we need to think more asynchronously. I believe David Keyes, who spoke earlier in the session, alluded to some important work that his group is doing along that way. And we just need to build into our new algorithms and ways of thinking less expectation for uniform performance and more expectation for there to be a lot of variability.
So Kathy Yellick often has a question she asks is, how dynamic do you need to be, right? It seems that all the options we're being given, it's either synchronous bulk calculation or throw it all in a DAG, and off you go, and everyone kind of finds your dependencies, and off you go executing. And there is a realm in between. So one option that we use in our code oftentimes is we call feedback load balancing. So in my example with the memory, you'd have the code just time how long did you take, and you just note the degraded core, and the next time you load balance, you say, I'm not going to give you as much because you're messing up. So if you have kind of persistent core downcycling, you're going to see more downcycling with these kind of dynamic frequency processors as they come online. You know, GPUs have this kind of symmetric multiprocessing is kind of baked in. Everyone ticks their clock at the same speed. But between different SM groups or between different warps, you might throttle up and down because hotspots are important. Intel already jumped off the cliff. Every core can muck with its clock. So all the dynamic cores can go up and down, and you just have to, you know, the problem with that one is it happens relatively quickly, right? Between one multi-grid and the next multi-grid solve, we can watch the clock change on us. But they tend to all go together right now, so we're not, although they could frequency change all of them, they don't often do it yet. But across nodes, yes, you know, particularly where the node is in the rack, you'll see that sometimes that node is consistently downclocked. So this kind of thing in the middle where you have to tolerate, you know, non-blocking things, but you might not need a full-up dynamic execution. So that's where I'm kind of landing right now. And then within a sub-chunk of your code, I think you can dynamically, you know, the more dynamically you want to schedule yourself, the more tightly you have to be able to see each other's memory, the more coherence you need. And getting coherent across a big machine is hard, but getting coherent across, say, one processor isn't so bad, right? I have an on-chip network that makes very fast coherence. So I envision, you know, the bigger the scale, the more you have to kind of bake in who does what, and then at smaller and smaller scales, like down to the core or even the chunk of a core, I think then you can be, here's a work queue, or let's do work stealing, or let's do something fancier, because you can get to each other very quickly.
Did you have a comment, Cameron? I saw you puzzling over that. Oh, okay.
I would echo the load balancing approach. We do that with our adaptive unstructured mesh techniques, for other reasons, but you certainly could implement a very similar feedback loop.
Okay, we're coming up on the last few minutes. I love that I didn't have to come up with any of my own questions here. That's great. Everybody had a lot of questions, but I did want to ask real quickly, just to go across the panel, a couple of questions. Strong scaling. How much does that matter in practice?
Getting to be more so.
Say that again.
It's getting to be more so.
Getting to be more so. Lois?
Yes.
We find that many of our users really are very concerned about strong scaling. Oftentimes they want to model some particular problem at a certain amount of fidelity, and they really need to scale in that way. Or they want to solve a problem and solve it faster, but there's a particular problem they have in mind. So strong scaling is quite important for many of the people who use our software.
Yeah, for production science, you want time compression.
So I'm sorry, I didn't understand that, Cameron. That's a vote for strong scaling?
Oh, absolutely.
Okay.
Yeah, and I'm going to disagree a little bit with these guys.
Yay! Thanks, Rob.
Right. Strong scaling is useful, but you have to be careful about how you read it, because I can give you an algorithm that has great strong scaling, and it'll be slow as heck. So you can't lose sight of the fact that you want to solve the problem quickly, or use as little power as you can. Then given that, strong scaling, to me, what it does is it tells you sort of where the sweet spot in your code is. If it's a coupled problem, it won't strong scale perfectly. It's going to roll over at some point, and it tells you sort of where the sweet spot is for parallelizing your code. And you'd like things to strong scale as best as they can, but if you're solving a physics problem that's coupled and you want to solve it fast, there's only so much you can do. So I think you have to be careful with it at the same time.
We tend to focus on providing these capabilities for science applications, et cetera, but in the long run, if we're really going to have an influence on the economy, et cetera, we really got to get industry using large-scale parallel computing and effectively, and they're not going to work with things that don't strongly scale, because time is always their critical issue, time to solution. Now, it may not have to strong scale to 1 million cores, but whatever they run of that, it has to be efficient and strongly scaled.
Right, but my comment was just that strong scaling does not mean fast necessarily.
Correct.
It just means that it goes twice as fast when you use twice as many
in fact, we well know.
But if it starts out slow,
if we got something good and slow, then it's often easier to get good strong scaling.
Right, and I think a lot of people get sort of fixated on strong scaling. I'm especially sensitive to it because I do linear solvers, and it's a very strongly coupled problem often. And people look at how hyperscales and they say, "Oh, this thing is terrible strong scaling." And we ask them, "Well, go find an algorithm that runs faster and come back and talk to us again." Because it relative to a lot of other types of algorithms, linear solvers really, and multigrid in particular, really does not strong scale well, but they're very fast algorithms. So you have to be careful.
Yeah, I completely agree with Rob there, and this echoes back to the point we discussed earlier about really understanding what you can expect for your problem and your algorithm. So building performance models so you understand how efficient you could hope to be is very important, so that you can determine whether you're functioning well or not.
Okay, one more quick question. MPI is a fairly large interface, right? It's got a lot of functions in it. Just ballpark figure, what percentage of the MPI interface are you accustomed to using on a regular basis?
I probably call about 10 of the functions. 10
of the functions, that's probably 1% of the interface.
Well, I'll answer to say that within the PETSI software overall, many of them are called at some point.
Okay.
I have the privilege of working at a higher level of abstraction. They're buried within the lower level. So I personally don't call them at all. I work with vectors and matrices that underneath the covers, do a lot.
Well, and that's the beauty of abstract interfaces.
Right.
Yeah.
I would say there are 5 or 6 calls that are 90 to 95% of the MPI calls, maybe 10 total that you really need, at least in what I've done.
Same answer.
Okay. All right, well, let's thank our panelists. It went really well.